Welcome, dear students, to lecture 3 of module 2b, induced EMF. We have already discussed what is Faraday's law. Whenever the magnetic lines of force linking with the coil or conductor changes, an EMF is induced in the coil. That is Faraday's law. You will be having a magnet and a coil in between. When the relative motion between coil and magnet changes, an EMF will be induced. And what is Faraday's second law? Faraday's second law gives the magnitude of induced EMF. Magnitude is given by minus n into d phi by dt. What is n? N is the number of turns. Delta phi, change in flux linkage in time dt. And we have studied about the Lenz's law also. That is, direction of induced EMF is proportional to, or it is in such a way that it opposes the basic cause responsible. What is the basic cause? Cause is change in the flux linkage. Due to change in flux linkage, EMF is induced. And as per Lenz's law, EMF is induced in opposite direction to change in flux linkage. So, we are writing E equal to minus n into delta phi by dt. So, the main principle of Faraday's law is due to change in flux linkage, an EMF is induced. Okay. And in this class we are discussing about induced EMF. Before that, what is an EMF? EMF is electromotive force. We know that in all the metal there will be free electrons. Okay, if you are applying a battery or voltage source between two ends of metal, what happens? These free electrons will move in a particular direction. So the electric force or pressure that cause electron to move in a particular direction is electromotive force. And the induced EMF means whenever the conductor cuts the magnetic flux, then EMF is automatically inducing. We are not applying a constant battery or anything. It is generated by relative motion between flux and magnetic field, or coil and magnetic field. Such type of EMF is known as induced EMF. It is classified into two types: statically induced EMF and dynamically induced EMF. Statical, as the name itself, stationary. Dynamical, as the name itself, moving. So, statically and dynamically induced EMF. Statically is again divided into self-induced and mutually induced EMF. And in this video, I am discussing about the derivation of dynamically induced EMF. Okay. So, first I am give you a brief idea on what is dynamically induced EMF. The voltage induced in the conductor due to relative motion of conductor and magnetic field. So, this is the basics of a Faraday law. There will be a relative motion between conductor and magnetic field. Then there is a change in flux linkage, as a result an EMF induced. Such type of EMF is known as dynamically induced EMF. That is, either a conductor, this conductor will be moving in stationary magnet, or this magnet also can rotate in this stationary coil. Okay. So, example for dynamically induced EMF is electrical generator. All the generators are working on principle of dynamically induced EMF, because in generator this either coil is moving or magnet is moving. Next is statically induced EMF. Statically induced EMF means, as the name itself, stationary. Coil as well as magnet, both are stationary. Then how we can produce the change in flux? Change in flux is by increase or decrease in the current. We are applying current through the coil here. By changing the value of current, you can able to change the magnetic field. Okay. So, statically induced EMF, EMF induced in the coil due to change in flux linked. It is known as statically induced EMF. Example is a transformer. Here windings are stationary. Magnetic field is moving around the conductor and produce the EMF. Magnetic field is moving by changing the current, not magnet. Magnetic field is changing by changing the current. It is mainly by self-induced EMF and mutually induced EMF. Next, we can see in detail about dynamically induced EMF. EMF is induced when the flux linking in a conductor changes. That we know. That is known as induced EMF. In dynamically induced EMF, two cases are there. Either you can rotate the magnet, or you can change the rotate the coil with keeping other one stationary. Here we can see this is the case of, for example, this is rotating the coil with magnet stationary. I already discussed there are two possibilities. First one is of DC generator. DC generator means we are rotating the magnet, keeping the coil stationary. And in AC generator, we are rotating the coil, keeping this magnet stationary. This is the main two examples of dynamically induced EMF: generator and alternator. In alternator, coil is rotating. In generator, field is rotating. So next we can see the derivation. So consider north and south pole, and you are having a coil here. Coil is represented by a dot, and suppose this coil is rotating at a velocity of v. Let v be, this is not the voltage, velocity. This v can be resolved into two portions. V cos theta, that is in perpendicular to direction of magnetic field. Magnetic field here, cos theta, this is in direction perpendicular to magnetic field, and this is sin theta, this is in direction parallel to magnetic field. So consider let L be the length of conductor. This is, we are discussing about the dynamically induced EMF, a north pole and south pole. Let L be the length of conductor. Let L be the length of conductor, and it is moving with a velocity v. Suppose you are assuming that it is moving a distance of dx in a small time dt. Suppose this coil is rotating a small distance dx in time dt. Okay. So what will be the EMF induced? EMF is equal to, as per Faraday's law, N into d phi by dt. What is d phi? Change in flux linkage, because this conductor is moving, so there is a change in flux linkage. Okay. Next we can see what is the change in flux linkage. D phi. Phi can be written as area into flux density, B into A. Phi can be written as B into A. So you can write N into D into BA by dt. What is area? Length is L and velocity is V. Since it is moving a small distance dx in time dt, what will be area? Area equal to length into breadth, that is length into the distance moved, length of coil into distance moved. So L into dx will be the velocity. So L into dx by dt. See, area equal to L into dx by dt. This is dt. So B into N into A equal to L into dx. So L into dx divided by dt. What is x? X is the distance moved. What is rate of change of distance or displacement? Rate of change of displacement is velocity. So you can write B into N into L into dx by dt equal to V. You can write dx by dt as V. Okay, so here it is written B into N into L into A. V is also there, so that portion is not in the screen area. B into N into L into V. When number of turn equal to 1, if you are using only one number of turn, then EMF is given by E equal to B into L into V. B, L, V be the EMF induced.
Induced EMF. Suppose the armature takes t seconds to complete one rotation clockwise. At time t is equal to 0 second, the armature ABCD is vertical with arm AB up and arm CD down. At this position, when the armature rotates, the rate of change of magnetic flux is momentarily 0.
That means at this position, when the conductor, this position of conductor is parallel to magnetic field. So this is conductor lies in parallel to the magnetic field. There will not be any change in flux because both are in same field. That is parallel. See, this is the parallel path and this magnet is also parallel. So there will not be any EMF induced.
Hence, the induced EMF at this position
Since
is 0.
No EMF is induced
During the first quarter
zero.
rotation, the induced EMF increases. Then at time t upon 4 seconds, the armature becomes horizontal.
See, in this case, the conductor becomes perpendicular to the magnetic field. So at that time, maximum induced EMF is generated. When it is parallel, EMF is 0. When it is perpendicular, EMF is maximum.
This position, the rate of change of magnetic flux momentarily attains the maximum value. Therefore, the induced EMF at this position is maximum. During the second quarter rotation, the induced EMF decreases. Then at time t upon 2, the armature again becomes vertical and therefore the induced EMF is 0. During the third quarter rotation, the induced EMF increases but has an opposite polarity as compared to that of the first half rotation. At time 3t upon 4 seconds, the induced EMF attains its maximum negative value. During the fourth quarter rotation, the induced EMF decreases and becomes 0 momentarily at time t seconds as the armature is vertical once again. So,
see, when this coil is parallel to the magnet, then EMF is 0. When the coil becomes perpendicular, EMF is maximum. If the coil is perpendicular in opposite direction, then EMF is negative maximum. In this way, you will be getting an alternating wave. So this is the note which I have prepared for you. Induced EMF. Induced EMF mainly classified into two types, statically and dynamically. Here dynamically induced EMF, either by magnetic field is stationary, conductor moving, or magnetic field is moving and conductor stationary. So you consider this field. This is the field, and suppose this conductor is moving with a velocity v. So you can resolve this into 2. This will become your theta. Okay, this is the angle parallel to this or in align with this field. You are considering the angle theta, where this conductor is moving with a velocity v. This is the derivation we have already discussed. Let L be the length of conductor. It moves a distance dx in time dt. Then area equal to what? L into dx. Phi, what is flux? A into b. So L into dx into b. This is the change in flux. That is BL dx is the change in flux. So what is EMF? EMF is d phi by dt. That is B into L into dx by dt. dx by dt is the velocity v. Since it is rotating at a particular velocity, you can write the equation for induced EMF as E equal to BLV sin theta. Theta is the angle of rotation. That is, this is the theta. When it is lying in perpendicular or parallel to the magnet, that is when theta equal to 0, it lies parallel to the magnet. Then what happens? EMF becomes 0. That is theta 0, EMF is 0. When theta equal to 90 degree, EMF is maximum. That is the coil is perpendicular to the magnetic field. Thank you.